We're going to get into a brand new style of physics today.
Sick.
Wait, where did I just put? Oh, there it is. I know, I owe you all homework, so at some point I'll reduce the amount of homework I'm giving and practice grading the ones that I have. Okay. Oh, this one's not as far back as the other one is. That's the, maybe I'll do back to the class. There we go. Hopefully you can still see that online. You have a meeting on the front. Okay, so I told you we do the most fun thing of all time. And we're gonna figure out how to see. Okay. So some of you have been, don't look at me like that. You want to see how to see, right? No. No? It's cool. You don't like it?
Ignorance is bliss.
Okay, that's a vibe. That's definitely a Thursday vibe. Maybe more of a Friday feeling, you know, to say to yourself, well, I don't really care about waves, like who gives a shit. But you like waves. So like, you know, basically what we're gonna talk about the knowledge that we learned from fluids, and then we'll also talk about the mathematical techniques that we sort of saw at the beginning of the semester. We were doing this thing called separation of variables. So we're going to use that today. And we're really going to begin to think about how these Maxwell's equations, this simplicity of this 4-equation structure is going to lead us directly to some unexpected results. And it's going to predict the speed of light for us. Okay. I know, seems unrealistic, right? So in order to do this, I want us to, you know, take a step back and to really think about the historical context. So let's go back 200 years ago. We figure out that magnetism is this stuff where you like have a piece of metal and that particular piece of metal tends to point in a certain direction. So you put a small sliver of it onto like a floating piece of water. You know, you put a little pivot on it and it tells us how to navigate. And they're like, whoa, that's so cool, right? And they're using this for navigation. And then someone else is like taking a piece of amber and they're rubbing it with fur and they're holding it near their hair and they're like, well, I can make my hair stand up, right? And that evolves into understanding of the electric force. So that's how you get Coulomb's law and Ampere's law, which is governing even before you have currents, before you have any sort of electricity flowing in homes, we're understanding how magnetism works. Okay. And we think about these two things as relatively unrelated, and then Maxwell comes along and says, there's some relationships here that we should investigate. Okay. So even though electromagnetic waves, which we're about to talk about, maybe you started reading it in the chapter, we're going to do it slightly out of order because I think that historically it's going to make a little bit more sense. We'll see. If it doesn't, you know, soon. Okay. So we've been solving Maxwell's equations for the distribution of charges. We solved things like Poisson's equation, and there are all these names that we're going to have to start to remember. Poisson's equation looked like this, maybe. Remember that one?
Yeah, doesn't it equal 0?
This is V. Oh. It does equal 0 in one specific case, but that's the boring case.
Okay.
Okay. So what we're basically saying here is something that we kind of said in computational. We said that if you have some distribution of charges, then you can figure out the vector potential, right? And that basically we use a relaxation scheme in order to just say, let's just guess the solution a bunch of times. But remember, now we're 200 years ago, you can't do that. Or 100 years ago, whenever that was the appropriate time. So there's no computers 100 years ago. No computers even like 55 years ago that you can use at home. I know, it's great. Okay. All right. So we figured out how to set this because mostly we had boundary conditions that we set boundary walls and everything else. And so let's have a look at what Maxwell's equations would look like in the absence of charges and current. So think about no charges and current. Okay, empty space. What are our Maxwell equations? There we go. What is del dot B? Good, that's the easy one.
Del cross is zero.
Sorry, say that again.
Del cross is zero.
Del cross E is 0. Is that true?
It's negative dB dt.
That's correct. So it was this. It was 0 when we were thinking about magnetostatics. But now we're adults. This is electrodynamics, this is magnetodynamics. And when you're ready, you can talk about, magnetohydrodynamics. You want to throw some fluids in there. That always sounds cool when you drop that in the bar. Hey, what are you studying? Magnetohydrodynamics. Oh, yeah. Immediately, they turn around and walk away. No one stays for the rest of that conversation. Okay. So that's good. You got half of them.
Del cross B equals.
But don't read them off.
Read them.
Okay. Del cross B equals.
U naught. Parentheses.
Oh, you're not sure.
So we don't have J's because we're thinking about free space.
Oh.
No currents, no charges.
Plus.
Oh, is that the?
That'd be really convenient, right?
Yeah,
If they look the same.
yeah, but you don't.
I just have one with J's.
What's that?
Mine just has J's.
Okay, yours just has J's. Interestingly enough, in order to get the units to work here, we're gonna do something very unusual. We're gonna do this. So it has sort of a similar structure, but that's not right. But it's not the same. And what's the fourth?
Del dot E.
Del dot E. And in the absence of any charges, in the absence of charges, why is it 0?
There's no charge.
There's no charge, so therefore the row would be
Zero.
0. Good, all right. Now we're really working with gas, right? Okay, so this is beautiful, right? No. I'm currently describing a vacuum. Okay, so you think vacuum, you think cleaner? No, what do you think vacuum?
Space.
Space. Okay, so space is no matter, no currents, no charges, no protons, no electrons, no neutrons, no matter, nothing. Nada, that's it. Zilch. Can I have electric fields and magnetic fields in there? Why not?
Because there's no charge.
But can they go through it?
Oh, yeah.
Yeah, okay. There's nothing permitting, nothing excluding it. If I see like a Faraday cage, you design those so that B fields and E fields can't go in. This is the opposite of that, right? We're saying empty space. We so far don't see any restrictions, right? Now, maybe we don't have an intuitive understanding. I certainly don't see an easy way to generate them. So I'm thinking to myself, well, normally I would generate with this. And I'd be like, oh, at least if I could make charges, then maybe I can move some charges around and I can get B fields. That's how I think about generating E and B fields. So this is not directly obvious, but we're gonna do some mathematical mumbo jumbo and we're gonna see something really unique. Okay. Okay, ready for math? All right. First one, and this is everyone's first instinct, of course. Let's take a cross product of this. And in particular, we're gonna do del cross E. Okay, so let's do that to the other side. That's gonna be minus del cross dB du dt. You have this identity memorized?
No.
It's
Really? Just gonna kind of expect you to have that memorized. I would have to look this up.
if it's six or green, it's better now.
Well, if you're taking a double cross. Square of what?
Not the right table one.
Oh,
Oh,
Oh, no, I do hear what you're saying, that's the del inversion, but we're not there yet. We may end up there. Right? I don't wanna see it again, okay, alright, so in fact, the identity here, this is identically equal to. The gradient of del dot E. Minus del squared E. And what's this?
0.
Why is it 0? Because we already wrote that down. Okay. Awesome, okay, so that's just this, and that's just minus. Del cross VB ET. Okay, are we SOL here?
What's that mean?
Shoot out of luck, yeah.
Yeah, shoot.
Well, I don't, yeah, I
Oh.
guess I swear on that, that's. So yeah, are we shit out of luck here? Can we get it into something that's more interesting? Probably not, we're done.
No, we have luck.
No, we have luck. There's more to be found here. We have other equations we use. So we tapped into this one here, we tapped into this one here, and look, I see del cross B over there, and there's del cross B over here, no?
Oh my gosh.
Oh my gosh. Can I apply the del cross B? Can I rearrange this?
Yeah.
yeah.
You can take the dt out,
Yeah.
right? And then you could do dt of whatever that is, right? Can you do that?
Yes,
Slow
as
down.
long as you're taking.
Yeah, so in fact, I can do this, right? I can say, or maybe I'll do it over here so you can see it. So let's say I do it on this side. Let's do the ddt's everywhere, right? Let's head this and we're gonna hit it with d dt. So then this would be del cross d b dt equals mu naught epsilon naught. Double what?
A squared.
What's squared?
D.
Del squared. Okay, interesting. So this now gets to go over here. And because I have a minus on both sides, we're gonna
Oh, I forgot.
get rid of that. And so let's read off that right hand side because that's what this is here. This is mu naught epsilon naught del squared E del T squared. Sick. Whoa. No, or yes? Yeah, I just wasn't sure if you said you're trying to get my attention.
No.
Okay, what does that look like?
All of it or just the right side?
Well, let's rewrite it then. What does it look like? Say we live in a magical kingdom in which there's only one spatial dimension. That's true, but that's not the first place you saw it.
Oh, sorry, complicated.
Running computational, that's correct. What do we call it there?
Couple.
Yes, we talked about like what type of differential equation is here. So I have two variables that I care about. That's why there's partials. I have a spatial and I have a temporal. And what order is this?
Second order.
Second order, right, okay. Okay. This is a specific type of second order equation.
Concavity. Oh, it is separable. Can we just?
We could eventually get there, because I hinted at that at the beginning, but this equation has a name.
Ooh.
Oh, is this like the specific one, like the one with like effectively, or del squared E over del x squared, is that the one? Okay.
What do you mean by that?
Well,
Imagine that it's not E, imagine it's any function.
well, you can get like a spatial, second derivative by understanding it's like, time derivative. I don't think it's,
Okay, the first time you saw this in computational, there was only one time derivative on the right hand side. And we said that this type of thing here described the concavity.
Mhm.
Right? And that we said with one time derivative, you would diffuse away whatever it was. And we used it for the heat equation, we used it for heat diffusion. Okay. And then when we had two time derivatives, we called it something new. We called it the wave equation. And we said that this gave solutions of waves in x and t. Okay. So in this particular circumstance, let's put this back. Get out of our la la land and we'll be back in reality. Okay, so this is saying that spatial derivatives and time derivatives have a relationship. We're going to try and investigate that. In fact, I only did E here, but we could play the same game of taking a del cross on this side, and then you'd have a del cross on this side, and you take a time derivative of this thing, and you end up with the same thing, but for E. Okay. Yeah. Do be crazy like that.
Does it matter, it's mu or is it just that mu?
Oh, sorry, look at that. Okay, so this is a second order partial differential equation, and they're coupled. Okay, one is coupled to the other because of our initial starting equations. Okay. All right. So we said, maybe it's possible for there to be electric field or magnetic field in this empty volume in space. And in particular, what these results show is the way that they will exist is as waves. Okay. And if you don't believe me that they're waves, we're going to do a big deep dive into wave analysis right now. Okay. So the two things we're going to need to dust off in our brains is wave analysis and complex analysis. I'm not talking about whether or not it's hard, I'm talking about real and imaginary. So generally speaking, this is the wave equation. Okay, let's write it like this. And we're going to write it arbitrarily. So that's going to be our wave equation. And this is psi. All right. So if you look up a book, you just ask Boas or you ask one of your math methods books, type into search wave equation, that's what you get. Anyone know what this is? The V. It's reasonable, right? It's super reasonable. In fact, that's right. Yeah. So the speed just is right here. Okay. So 1 over v squared, you could rearrange that and you would say something along the lines of the velocity in this wave equation is 1 over the square root of mu naught epsilon naught. Okay. And so I promised you at the beginning of class, I said that we've been doing all this weird stuff with amber and metal that points towards the north, and they measure independently epsilon naught. They measure independently mu naught. And then they multiply them together. They take the square root and they take 1 over. And what do they accidentally get? C. Okay, very unexpected result. They're like, whoa. And then they post that on TikTok and they get like 6 views. Okay. Alright, didn't exist back then. Alright,
They put it on their YouTube channel.
yeah.
That's 6 views.
Well, that's 6 views, yeah, it didn't exist, that's fine. Just a quick question here, if there were mediums, do we know how this would change? Like if this was inside of a medium?
Just you have that, so.
And so it turns out that V here will also be appropriate when we think about distributions of charges, we'll have to do it slightly differently. But the only thing that's gonna change is that rather than the permittivity of free space or of a vacuum and the permittivity of free space and permissibility,
Yeah.
whatever, yeah, call it. You know what epsilon not, you get it, alright. Okay, so let's look at some solutions. We've seen this problem before. We're gonna try and attack it in a very similar way. When we have v squared in chapter 3, we use that up there. So how did we solve this equation in chapter 3?
Back in chapter 3.
Integration. Was it, did you have like initial condition?
Yeah.
Yeah, at some point we'll have to have initial conditions to make sure we get the boundaries right.
Mhm.
So one of the tricks to doing math at the highest levels is being a good guesser. Okay, so we look at the functions, we look at partial differential equations, and we think about the way that the different terms interact with one another. And we say, okay, if I see two spatial derivatives, I need to use this type of technique.
That's right.
If I see two spatial derivatives and a time derivative, I need this type of technique. And so the actual partial differential equation or ordinary differential equation is lending ourselves knowledge about how to solve it. So in this particular circumstance, we might look at this and we say, well, this might be a function of t, but it's not clear. It doesn't seem that important. But instead, we might say, well, this is some constant, some distributed number everywhere. So I'm taking some partial differential equation, I'm gonna find some function in space, and I'm just going to guess that x does not impact y, and that does not impact z. What's that technique called?
Don't remember the name of it, but don't we use like E as your function? Or sometimes we could use like a trig function, Euler's formula.
It's helpful to remember the name because that'll tell us what to do.
Yeah.
Wait, here you would say.
I'm gonna guess that x does not impact y,
Like on solid.
that y does not impact z, and that I'm gonna solve this 3 different times, because we're gonna remember what this thing looks like, right? This thing here is gonna look like del squared x plus del squared y plus del squared z.
All separation variables.
Aha, okay, so the fact that you have 3. What?
Variables are separated.
Yeah, so that's what you wanna do, right? So we're gonna make a guess, right? And we're gonna say, okay, is this reasonable? Is this gonna work out? Okay. So that's how we would solve these. And we've done this a bunch of times. We did this in computational, you did this in E&M1, but now we're gonna make it more complicated. We're gonna add a 4th dimension. Ugh, disgusting, right? Okay, so now I have T. And I'm also gonna make a guess. I don't think T affects any of the spatial stuff. Okay, and we're gonna see how far we get, right? I mean, I know how far we get, because I've already, pretend. Alright, so let's make a guess. How am I gonna rewrite psi, which is a function of, and let's just imagine for a moment that we're just doing z. We're not gonna do all those spatial variables for a second. Okay, so we'll do z and t. How would I write? Nope. The first step of separation of variables is to
Right?
separate the variables. How do I do that?
You have like 2 separate terms.
Okay, say that better. Say,
Yeah.
give me more.
Yeah.
DT we put to one side and he seems to be.
Okay, so we're gonna say it like this,
Yeah,
okay, and we're gonna put the Z in this one,
yeah,
we're gonna put the T in this one, and so what's this?
plus.
No.
Minus.
No.
Times.
Times.
Yeah, okay,
Times,
okay.
okay, and this will be T. T of T, and what's this one?
Z.
Z of Z, very good, oh wow, good job, Tim. Alright, Z of Z, you see? Okay, awesome. Now, why do I like this? Well, I like this because when I plug it into my differential equation, I'm gonna get copies of it back. And I know that getting copies of it back always lends me to what type of solution?
Right one.
What's it? The right one?
Like a,
Say that again.
yeah, that,
E of X. Okay, so I really like E of X because every time I take a derivative of it, I just get the same thing back. Except for if I need a little spice, right? If I need a little like sauciness, maybe I need a little something out front. Right? But the minuses and the plus, especially if I'm taking two derivatives, doesn't matter. They're gonna flop back and forth. So it doesn't matter what my solution is in the top of the E of X, I can even do E of minus X. Because I'll get the same thing back with two minus signs canceling to become a positive, right? So knowing how these individual functions work ahead of time says, well, you know, maybe this is gonna be the product of two exponentials, right? And that could kind of work out because then I'd mostly get the same thing on both sides with some junk. And all I'd have to do is just connect that junk to something meaningful, take those constants and like give them interpretation, right? Okay, so that's the goal. Okay, this is how you're supposed to think as a physicist. Don't think like a mathematician, no offense. But in this class, we're just gonna wing it and we're gonna hope that it's right, okay? Mathematicians have to prove stuff, we don't have to prove it, it just has to work. It has to represent the real world, okay? So here's what we're gonna do. Okay, we're gonna say this part here, let's do the spatial derivative, we're gonna assume on this side that it's only the Z derivative. Okay, there's no such thing as X and Y, they never existed in all of our life. Okay, so how do I write that? We're gonna do del squared, del Z squared of Z E equals 1 over V squared del squared del E squared of Z. That's right, awesome, 100%. What are we doing?
he would go away on the left side.
What do you mean go away?
So after you take a second derivative of it, it's not gonna stick around. Or no, I guess it's a constant, damn it.
That's why we don't want to plus them. Right, if we add the terms, you see what exactly happens is that you would lose any information about this thing. So if we multiply them, now of course there could be more than one term in here, I don't have a problem with that. But if I have this BZ and I apply it to this, it only affects which one?
Just the Z,
Just the Z. And what happens to T?
it's just a constant.
Alright, so this comes out. And on this side?
So,
Good, okay, so let me rewrite this, okay, T of T. D squared, DZ squared of Z, big Z, and I'm not gonna write the little one inside anymore, lazy. Okay, and that's equal to big T over V squared. Del squared, del T squared of. Wait. Of big T. Okay. So we're almost to where we want to go. We have to do one more trick. Why would we want to do that?
Oh, it's these stuff on the left.
Yeah, right. Let's clean it up. Let's make it nice for ourselves. So let's divide both sides. And we're going to do 1 over ZT on both sides, 1 over ZT. And then that cancels. And this cancels. And now T's on one side and Z's on the other. Right? That's beautiful. So now I have 1/z del squared del z squared big Z equals 1/t v squared. And I know what you're thinking, that's not real TV. About that, that's it, right? We're basically done. No, okay, so we're not done. So what's next?
Hansen solution.
You're almost there. You're almost ready to guess. We're almost ready to guess exponentials. But there's actually one step that's going to teach us that it's exponential. So we kind of had a hint because we could separate these things. And we had a better hint because we knew it was a wave equation. To me, how dare you? This is a partial differential class at this point. Integrals won't happen for at least a couple weeks. Integrals are hard. I don't like doing them. I'm not good. Derivatives easy. Just cosine becomes sine. Or something. Okay, we're almost ready to take a derivative. We're not there yet. There's one thing we want to notice about this relationship.
The difference of these squared, with respect to time.
Sure, but look at the left-hand side. So you said you wanted to put all the z's on one side? Why? That's for funsies? Yeah, symmetry is beautiful, but is that all we care about?
To relate z to t.
Okay, so we're relating z to t, we're claiming they're independent variables? So let me ask you a question, is there t on this side?
No.
No, we did our job. Is there a z on this side? No, we did our job.
Oh.
Velocity might have.
No, velocity is a constant. We don't even know what velocity is, it's 12 or 7. Right, some garbage. We'll figure out what the velocity is later. But generally speaking, right, we don't know anything about this wave. We've never even heard of E or B fields yet. They don't exist. We're just talking about how we treat waves in a day-to-day math life. But I have here on this side something that only depends on t. And I have here something that only depends on z. How could they possibly be equal to each other?
The same function.
So are you saying z is t?
You could say that. I would love to say that.
No, that I mean that might work in one specific case. It's very boring.
Yeah.
Said so, I don't.
You said they were equal, Charismatic. Okay, they are both equal to each other because they are both constants.
Okay.
Watch. What? Hey, watch this. Or actually, let's do it more. What? Charismatic, stop it. Okay. So I'm going to make a very strange claim here. Okay. So the function is t. T could be whatever we want. But when we do the function and we multiply it by its second derivative, I only get a constant back. I know, it's unfortunate, but it's true. Because remember where z is. Z is on the bottom.
But it's still changing probably from the fun.
Sure, but which function, when you take two derivatives, gives you the function back?
Oh, you're saying E over
Yeah, so e over x is 1. And over here, if I use the same type of solution,
this.
that's stupid, it's not even fun. Okay, so this is how we get here, right? It's not by like some, well, it is magic, but it's math magic. It's the best type of magic. Okay. All right, so on this side here, we say this whole thing is a constant. This whole thing is a constant. So let's solve both of them separately, because we are separating the variables. Hey, it worked better today. Someone sneeze. I saw that. Just driving me crazy. Alright, so write down for yourself with the solutions.
What Z is?
What's Z is Z? Generally.
I think
Anyway.
you get.
That's,
I've never really get negative.
Oh my
signs,
goodness.
Yeah, I mean, I think you're right. I just feel like.
But you can take out a negative 3 points. Positive. Oh, wait, here, watch this.
I don't have any idea.
What? This. No, because then it would be divided by the.
Okay, yeah.
You can ask one another.
Maybe.
In.
No, in case of conflict, you just ignore the bad disease.
Sure. But there's a game that I want to play. If it was just like.
We want a generalized solution. So we're gonna have multiple solutions, we're gonna see which ones work and which ones don't. Right, we're gonna look at the style of the solution. Alright, kids, what do you got?
And KZ square root of I.
Excuse me? Say that again? Yeah.
And the square root of I times KZ
E to the square root
of I.
Then.
of I.
And then KZ.
What's the square root of I?
You said you wanted a negative number, when I just made it negative, it just became positive.
Okay, I see.
It says negative K squared, and I wanted a K squared.
Okay. That's an interesting choice. And we'll talk about this type of solution in a second. But is there a better way to do that for getting a minus back?
Maybe, I don't know, yeah.
Just do.
No, so as she said, when she does I twice,
It's
I twice
negative
is
one.
negative one.
I twice is negative, right? So is this gonna work? If I, hold on, so let's do this one here.
It would just get us I. Right? We took it.
I was negative one.
Okay, so this is equal to,
I squared is negative one. I squared. is- You just say that stuff.
I forgot what ions means.
I is just
Right,
get rid of
square
negative.
root.
Oh, so it's just I.
Yeah.
I think
that's
it's-
the
yeah.
I thought I was negative one.
we can find out, we can find out in 1 second, right?
We'll
So,
find out.
let's do this here.
One is I. Hello? What's I? Damn it. Okay, then just take the square root off, that's.
Yeah, good, alright, so we did it though, right? We figured it out. Alright, so let's take the square root off everywhere, because all I have to do now is I just have to do something like this. And I don't even have to change anything for the derivatives,
Yeah, you just.
right? And so I'm just gonna bring them around everywhere. All my friends are now i's.
Can't do all of that, it's in just leaving.
Well, you had to write it anyways. Well, no, you just gotta see it through, you gotta see it through, you know? No?
Yeah.
No, sometimes with math, you have to go down a path for a long time to realize you fucked up like 20 minutes ago. Now, I don't think you should always do that when you're under the gun, you know, you're like trying to get the homework in, but it's helpful to just like do the wrong derivation for 10 minutes. You know, okay. And this is. Whew, that was fun. Is that the only solution?
The lower.
You say probably?
If you make
Was
it.
that what you got?
No.
What'd you get?
I just want
Make it
But what'd you get?
negative.
solves for gay. Got mine.
Make it negative.
What's that?
Make it negative,
Make what negative?
the exponent.
So you just you wanna ignore the fact that you had a solution that worked?
Well, you can have another one if you put a negative on it.
I asked for a general solution, okay? So I'm asking currently, I want us to think, that's why I gave all of you. So I was hoping that some of you would come up with one, other people would come up with another, right? So how would I create a generalized solution? You like this form, we're like, oh, if I get the minus in here, then I'll get it back because I'll get 2 minuses and it'll still be in the right order. But I wouldn't just say, you know, that's not right. Right?
It's,
You just put a negative in front of your I.
Negative from what?
The next one.
Here?
No, like below.
Oh, I see, by applying a negative in the exponent and then having I in front of the E.
just like.
You were the
one of
obvious and maybe
solutions, so negative some.
You do that.
You tell me.
I think so.
Okay, let's do it. Okay, so he wants to get rid of the I. He wants to put E here.
Yeah.
Like that.
Okay.
Okay, first time that happens. Okay. Okay, second time that happens.
And would it be squared, but then when you divide by z over there, the negative sign would go away?
Why is Frank?
Hold on, you're right. The -1 is here. This one is negative. And this one is negative, right?
Nice.
But if you divide.
But
by
watch,
z-
hold on, watch, ready?
I have.
You did it wrong.
Yeah.
Because look, this is what we're trying to solve now.
Yeah.
So essentially what I'm trying to say is del squared of del z squared of z is equal to minus k squared z.
Yeah.
So here's your z.
Oh.
Your z did not give you back your z.
shucks.
Ah, shuckers. All right, let's do that again. That was an invalid solution. Okay, I like this one. This one we know works.
Is there another one that works? I can't come up with another one. Just tell me the answer.
Yeah.
Tell me the answer. ChatGPT. I don't want to learn. Hate learning. Okay, so when we're thinking about multiple solutions, we can like toss in letters that we like. Right?
Why?
Sorry. We can't put Y in when we're gonna use Y later.
So be good.
I with prejudice, okay?
M,
Q.
M,
M.
I'll take M, one of my faves. Why do I wanna put it there?
Because it's the first letter of your name.
Also now says me.
That's gonna be the con.
Me,
Me X, yeah. All right, good, so let's do that, and where does that get us? That's IKZ like that. We're done,
Constant, yay,
that's the constant.
yay.
You get one constant per a bunch of derivatives. That it?
Is that it? Like, can we do more?
Probably use a trig.
Yeah.
You had the solution earlier, and I liked it, but not when you said it. No, sorry, what I mean is that it's appropriate, but not when you said it. You know?
Okay.
Yeah.
Do
Do you remember?
Like Oilers or
A little bit before that.
oh man.
We were thinking about separating variables, and you said instead of times,
Oh, adding it. Yeah.
because. Yeah, okay.
Oh my gosh.
So remember that any one term that we can apply these derivatives to, we can apply to each one individually. Right? So each one of these can be an independent solution of the differential equation. Okay, so what's the next one?
Probably a negative exponent.
Now we like the negative exponent. So let's try a new variable. Let's do n. Does that work? So this one becomes minus I. So I get a minus I here, minus I there. And I'm not gonna bring the n along because we know that that will work. Okay, this piece here becomes minus I. This one was minus, wait. Del squared of that. So I get 2 copies of this and 2 copies of this. And that is You tell me.
Why?
what's that? It's what?
It's positive.
It's negative one.
Which one of you? One of you is right.
Oh, it's -1.
Why is it -1?
So I times I is -1, and you have an additional negative, so it's. Wait,
Negative is.
wait a second.
Square becomes positive, but inside there's a negative.
Yeah, hang on, sorry. Let's just
Let's do
expand
this
it,
like this.
let's expand it.
Okay,
Yeah.
-1. Where?
Yes,
I squared.
there we go,
This is
just one,
plus.
yeah,
This is
negative.
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 Plus
Okay,
times negative is
negative. Love it.
negative. So this is also a good solution. We like this solution. Yay. Okay, is that it? Is that it? I want you to pull deep inside of yourself. Think back to yesteryear. When you first learned the mean of a deriv.
One
What does it
over-
mean, deriv?
You take those.
What's that?
Slides and sliders go.
How would that work?
Oh, yeah, they are.
Boiler.
Oh.
Sorry.
Just let him finish cosine. What happens if we take a derivative of a cosine?
This is awesome.
Yeah, either negative sign or sine, I forget. And then you take a derivative of a sine and you get cosine.
Yeah, so taking it.
Oh, so you get minus the formula back.
Yeah.
Isn't that what we want? Oh, so you should have come up with kind sines and cosines first. Said you had to make me learn what an I was. I had to remember what exponentials are, and those are super hard. Okay, so we're claiming that maybe these solutions work. MNO.
Nice.
Yeah or no?
I guess.
Does it work? You show me, do your derivatives. What goes inside of here?
Something can be,
You can tell me.
I just don't know.
Something crazy. It's not gonna commit.
No, forget, but what is it? Can't do this.
I don't.
Yeah, that sounds right. Okay, no, KZ, so that way, otherwise it would just go. Yeah, KZ, sounds right.
It's probably I.
So then, well,
Why? We don't.
or,
know.
or,
It's negative.
let's KZ, let's do this. But we do want negative to come back.
Yeah, it's back with the signs.
Well, which one has a sign?
Well, so it'll go sine, cosine, negative sign. Oh, maybe that works.
What if
Well, but both sides have a negative.
Cosine will have, cosine will have to have a negative in.
They both are gonna have a negative derivative, yeah.
Sine
one of the?
of KZ.
Yeah.
Just write it down.
Okay.
Did you do it? Do the derivative. Show me that it works. Hate it. I hate working in class. Don't like engaging my brain.
Yeah,
Yeah,
sine
yeah.
works. Yeah.
You guarantee it?
You put your life on
I
that?
think my paper says it. That's as close as we ever get in life. Paper says it, you must stand by it, right?
Derivative, well,
That's true.
Considering the derivative cosine. Yes, I got it.
Oh,
this
I have a
is-
really good way of remembering which
Yeah, that's what-
direction that you would have to go, and it's like with like a
they both have a negative.
cross, you can think of it as cross,
Oh, yeah, there you go.
sign is positive, and then negative below. And then on the, for you would be the right side, it'd be negative cosine, or no, positive cosine and then negative cosine. I can draw it on the board too, to make way more sense.
I'm not gonna remember that.
But clockwise is derivatives and then anti-derivative is counter.
Ah,
So that way, like the direction you're going,
so that would, yeah, okay.
Yeah.
That makes sense.
yeah.
That's a pretty good teaching tool.
Yeah,
So what do I put in here?
that would, for cosine, you put negative KZ.
False.
What, or sorry, sine is KZ. Sine is KZ.
The cosine's negative KZ?
They're both.
Hang on.
They're both casing.
Oh, yeah, you're right. Yeah, hang on, because cosine,
The negative comes from the fact that the derivative changes.
yeah. That's right.
Z is a variable.
That's right.
Z can get positive and negative, right? The function itself is the one that's doing the changing.
Yeah.
So if you put in a negative Z there, what happens? You just switch to the axes. It's the same solution. Right? Only time that it matters if you put a negative there is if you're taking away from something else. Right? If you said, 12 minus Z, that's obviously very different than 12 plus Z. Right? But if it's just the argument in there, you're just switching. All right. So now we have fully understood this part and we're super good at this for geniuses. What's kappa?
What now?
Oh, the.
That is a Greek letter.
It's a Greek letter. Let's ask a different way.
Ooh,
Love it.
Love it. We hate it. Where's mine?
The oil or this man or something, or this man,
Hold on. We gotta
yeah,
like that.
like
That.
there is.
with the negative.
Oh, good.
Yeah.
Yucky, right?
Yeah.
So what are the solutions for T?
I-
It's well.
It's one of those to solve.
Is this gonna have the same type of solution as that one is?
I mean, I feel like it can, but now you have a B and a K to worry about.
You had a K in the beginning.
Well, yeah, now you have A, B, and K inside of your function, right?
No, that's.
Right, but you want B squared to come out of it.
So just add it, it's like, or
What's that?
incorporate it into your previous solutions.
Wanna just throw B up in there? Wanna
Yeah, just put V along.
just let it be B as well. Yeah, I, B,
Well,
K.
you said there's,
Will it help our brains if we do this?
If you made it just one term, oh, huge,
Yeah,
huge.
Is that okay?
yeah,
Yeah.
You're not gonna cry, right?
Yep,
no,
and now you just,
Still wanna cry.
you just make it omega for where those are heading. So where you saw K before, you put omega instead.
So you tell me, what's the first letter here? T of T
Yeah,
is,
I don't know, I guess not one of those letters. A,
no, we would keep going, Q,
oh, okay, there we go. So Q, E, Y, omega, Z.
ah. Is it Z?
Oh, snap. My fault. Just drop the, yeah,
There we go. Okay, and
same thing, but
L, N, O, P, Q.
R, S, T. This is so weird.
just like, anyway,
Well, then you have to do the function.
Keep
Keep going.
Negative I,
Negative
omega T.
plus S sine.
Sine
the middle term says root it.
omega T.
What?
Omega T.
Thanks.
Or as T.
oh, we're.
Wait a second, why is,
V.
oh wait, skip over T, just
I
make
have to
it
skip T, right?
make you.
A,
No, go back to A.
A,
Okay, S, T, U, do we have a U? We haven't used the U yet.
Yeah,
A.
It's not.
That's a big U, you're gonna be able to distinguish that, right? And then this one is cos. Of,
omega T. Nice,
okay. What kind of solutions are those, folks?
general.
Shape do they have?
Uh,
They're waves.
yeah,
That's why it's called the
wave,
equation. Oh, because the solutions are waves. Okay, so let's think about this in practice. So now we also made this wonderful statement that says that somehow omega is kb. Okay. What do these things mean? Yes, but they have meaning, and I'm gonna teach them to you.
We're still assuming that B is equal to mu naught epsilon.
You don't know anything about fields right now. Fields don't exist, electromagnetism doesn't exist, this is just a mathematics class.
left.
D.
Okay.
Speed. Speed. Which one's speed?
K.
Ooh,
No, don't do that to me, don't hurt my heart. I use the letters in the right order on purpose.
Mhm.
They're supposed to look like what they are.
mhm.
So what's V?
B is like.
Speed, thank you. Good God, okay, so this is your speed,
Linear velocity.
sometimes we call it velocity.
Yeah.
Okay. And then this one,
That's
Velocity.
angular
Velocity.
velocity.
Wow.
Okay, what's this one? One's a sneaky one.
That's like the
Thing.
converter.
It's the converter,
Yeah.
that has a. That's like the thing, the K that's in there. It's like when it's bad and then you make it good.
Yeah.
It's. I do like that, but we're not using that as math.
Is it angle or wave number or which one?
Wave number.
That's right, that's right.
Okay, this is the wave number. Va bene?
What?
Okay.
Va bene is it good?
That's it.
Okay. So now we're almost there. Sometimes you might want to take that angular velocity and turn it into a frequency, just because you're like in the mood for that. So you might say something like
Yes.
Well,
cool. Okay. So is this the solution? How do I get to a place that I'm happy? Not like in life, because that's impossible, but like right now.
Solution is your happy with.
Yeah,
Yeah, you
I wanted like a general solution, right?
gotta multiply it down.
You know what?
Multiply.
You gotta multiply them together. Okay, so that looks like it's about to be a nightmare, right? Yeah. I like it. Okay, could be a nightmare, maybe not.
Do we set initial conditions to eliminate some?
Excuse me?
Set initial conditions to eliminate some of them? Boundary. And make-
We don't have boundaries, we're in free space.
true.
I'm pretty happy.
You're happy? We're stoked.
Let's make it.
So are these the same equations? These ones and these ones?
Well, like, yeah, but it changed very.
Now Euler's matters, right?
Okay.
Okay. So while these do fit the differential equation, they're the same solution. So is it necessary to have the negatives and the positives and the signs and the cosines? Not generally. Right? Okay. So we could go back to Euler's equation, we could write it all out, but we're just gonna say, let's pick one or the other. And currently, I'm gonna pick Euler's version, this version here, because I see something really pretty with exponentials. Now we can do it with our sines and cosines too, but it's not as elegant, in my opinion. What happens if I just take these pieces here and I multiply them?
Oh,
I guess M and Q are like now next to each other.
Okay, let's multiply those ones first. So we'll do MQ.
Then you have like negative KW.
Sorry, how do I multiply exponentials?
We add
Add them.
Just kidding. We add.
So I get I,
That's right. The whole point is.
P equal to omega t.
KZ plus omega t.
Yeah.
Beautiful. And next?
NR. Negative R. KZ plus omega t.
That's,
We're done?
I mean, it's like we can keep doing it.
What?
Not an affinity.
That's
Euler.
That's what we're.
That's what, oh, but that's okay, we can write Euler's after this. You're exactly right.
Yeah, yeah.
But this is what you wanted the whole time and I wouldn't give it to him, so I just wanted to be justified by the end. Okay? Alright, what's the next one? Is there another one or are we done? I guess based on the way I said it, right?
Yeah, we like. That,
Oh,
Finish that thought?
MR.
Oh, the cross ones, right?
Yeah.
Because they're multiplying the whole thing.
Yeah.
Okay, so now I'm gonna go MR.
Negative. Wait, you're adding them. Hold on. KZ minus omega t.
Ah, okay.
that works.
And,
Was it
so
Q N? And Q, I guess. I.
Minus K.
Yeah, and then what he said, yeah.
Or KZ.
Okay, let's keep it in order. KZ,
negative KZ.
negative KZ,
What do you
or are
think?
we changing the signs?
Okay, fine, Nick.
Oh, okay, cool. That one.
Okay. I know you hated that, I know that was really upsetting. Okay. So let's have a look at these solutions really quickly. What are they? They're
You can factor on again.
what I mean by this is what is the functional form they have? Cosine sine, so they're waves propagating in T or in Z. You can have standing waves, you can have moving waves. You don't know this, but you will get a sense of it. You have leftward propagating waves. You have rightward propagating waves. Waves propagating in time, right? So the different signs tell you which way as T gets bigger, it's gonna move. As Z gets bigger, it's gonna move. Okay, is this the total solution?
Just the Z.
Right, so you'll have to do it again, the X and Y. And we have a problem. It's a really, really frustrating problem, ready? All these M, Q, N, R, M, R, Q, N. What?
We don't know what they are.
Well, we don't know what they are, they're constants, sure. But I could just as easily call this like A0, A1, A2, A3. And I could add another one of these with A4, and another one of these with A5, and another one of these with A6. You can add as many terms as you want, as long as you change what's in the front. Right? Think about it this way. You can have one wave with a big amplitude, and you can add to it a wave moving in the same direction with a smaller amplitude. Right? Because those waves both will satisfy this condition. And that's the superposition of waves, right? We can add as many waves as we want to make a generalized wave solution. That make sense? Yeah, there'd be like a Fourier analysis, right? So this is the Fourier sum of all of our coefficients. So generally speaking, we're gonna have something that looks not like this. In the front, but something that looks like the generalized solution in Z and T, ignoring, of course, something like this. Oh boy, what did I say? I said, oh god, I shouldn't erase them. M, K, R, K. Wait.
Yeah.
I get
Yeah.
wrong. MQ, was that the first
Oh,
one?
yeah, I guess so, yeah. You.
And the second one was
And R. With K terms.
these are coefficients who have the wave number.
Okay.
Because I'm summing over K,
Okay.
Okay.
right? Did you say okay? Screwed. And then I forget which one this one was.
M R. And then it was Q N. No, it's Q. It didn't like Q.
C'est bon. That's it.
That's it. We can go home.
Okay. So that's your generalized wave equation for Z and T. So when we write it in this form here, function Z comma T, we can always think of that in the context of. Did I just did tiny things about this? We can also write this piece here as Z minus VT. Same way of writing it. For a wave equation. So if I just go some distance away, I'm gonna get the same value back. Right, that's the definition of Z. Okay. Did all this before, we did all this. We're about to learn about, we have time to do complex, yeah. So for this one here, if I'm thinking about this in the context of the words that we used before, the speeds, the velocity, the wave numbers, and I'm just thinking about it as sines and cosines. Imagining that we have a cosine. Okay. If we have a solution whose kx minus omega t, which direction is that going?
Forward and X backwards in time.
Well, like, what's the overall direct? Well, it depends on, doesn't it depend on like the actual, like, how you can.
Does it depend on the values of CNT?
If you're asking for the overall direction.
Yeah, as it propagates in time, as time increases.
Oh, it's not
Would it just-
increases? Oh.
B in the X direction.
What's that?
Then you said so KX minus. maybe?
So let's say we have some function, right? So these are sines and cosines, for example. And we said that these are either up or down propagating waves, this is the direction. Which ones of these are up and which ones of these are down?
Oh,
Just based off of their sign.
Yeah.
Just say
the one, is it the?
up, down, up, down.
Say up, down,
Yeah.
rude.
I think confused one is up.
Because we're just guessing? No, we can do it. We can write it out. Now you can use your graphing calculator. Watch. Right? Most of you have computers in front of you? No?
Mine died.
Oh,
Yeah,
Oh.
it's okay.
the paper never dies.
That's true. That is true.
Reach.
But which way did they go? Yeah.
Would the second one be up since a negative I? Because the I is a negative one.
That's very positive.
Yeah, so there's a different question. I'm talking just about inside here.
Oh,
The role that I plays outside is gonna be a little less obvious. We're first talking about this one, because there's two sets, right?
So the MQ one would be going up. As the.
Why?
Because no matter the value of T, as T will increase, it's always gonna be adding onto it. Onto the T.
Nice.
Isn't this a circular function? It doesn't always go up. It goes back to zero now.
Do we have to keep track of its domain?
Okay. So here are the rules, okay? I'm just gonna give you the rules and you can interpret them at your own, on your own speed. So omega is a frequency. This is always positive. Okay. K can be positive or negative. V can therefore be positive or negative. Okay. Omega equals KV, we said that. So if V is negative, then K is negative, because omega has to be positive. Okay. If it's positive K, then it goes to the right. If it's negative K, then it goes left.
That just could e to the X goes.
Well, remember that these are not just e to the x, they're e to the ix, which are really sines and cosines. Whenever I see e to the I blank, it's not really what it looks like. It's a wave. Okay. Make sense? You wanna know what W is? W is always positive.
W is always
It
positive.
has to, right? Frequency.
Okay.
So this has to always be positive.
Okay.
The only thing that can change is the direction of the wave and the wave number. But they're gonna be correlated.
Got it.
So you can't have a minus frequency, that's not meaningful.
Okay.
Okay. Okay, we're running out of time, so I'm glad I didn't actually get to complex analysis, but we should really think about what the complex analysis is going to be, because I want you to brush up. Because we're gonna need to pull out these things called the real and the imaginary parts of our complex functions. And then we're gonna make them into meaningful objects. Okay. Questions, comments, concerns? Okay, we are gonna have a rally. The faculty are having a rally for striking. So if you're pro us going on strike, come in and join us and shout at the
Like the art thing.
yeah, it's gonna be over by the building that they're building. It starts at 11 or starts at noon.
What plans?
You could have an advisory for good still.
Yeah, better fit.
With him.
It's not, it's
Perhaps.
Campus, it's the entire CSU.
And we're not on strike yet. We're asking, you know, if you don't put your shit together, you're gonna go.
That's this month of
Next
October.
week.
What's that?
Not this month of October. Cause like you were talking
So